So good morning, and this is a problem which is being provided to you for your finding out solution in the test actually. And most of you have asked for how the problem can be solved. I have solved the problem and I am going to discuss it through this video lecture. Now see the statement of the problem. It is compensate the system with open loop transfer function g of s is equal to k by s into s plus 1 into s plus 5. And the specifications provided are damping ratio zeta is equal to 0.3 and settling time ts is equal to 12 seconds for a 5% tolerance band. 5% tolerance band. So your formula will be different. And the velocity error constant is greater than or equal to 8 second inverse. Now we know that you have to proceed with the lag compensator, and you have to find what is the value of k. So using this kV specifications, we write the formula for kV. kV is equal to limit s tends to 0, s into g of s h of s. And your g of s h of s is provided. I substitute that k divided by s into s plus 1 into s plus 5. This s gets cancelled. I think I can choose a different color. This s and this s gets cancelled. So now replacing s with 0, I will get k by 1 into 5. So that k is equal to 50. K is equal to 40. 8 into 5 gives you 40. So now the transfer function is 40 by s into s plus 1 into s plus 5. For this transfer function, you are supposed to find whether you need a compensator or the system satisfies the provided specification. Otherwise, we have to go for a compensator design and make the system satisfy the specification. Now we have to check I have to design this based on the body diagram. And first we have to draw the body diagram. For that, we have to check whether it is in a time constant form. This s plus 5 is not in time constant, so we take f5 outside. So 5 is been taken outside. Now this becomes 1 by 5. This becomes 1 by 5. So obviously, this s plus 5 becomes 1 plus 0.2 s actually. This 5 when divided 40 by 5 becomes 8 divided by s into s plus 1, 1 plus 0.2 s. Now this is of time constant form. The next step is to substitute s is equal to j omega. So substituting s is equal to j omega, your actual transfer function becomes a sinusoidal transfer function, and it looks like this: 8 divided by j omega, 1 plus j omega, 1 plus 0.2 j omega. Now you have two corner frequencies, and based on their value, we have to arrange them in the ascending order. So omega c1 is the corner frequency of the first term, which is having lesser value compared to that of this. So it is 1 radians per second. Now this is the time constant. So 1 by 0.2 will give you 5 as the frequency, corner frequency. So this becomes the second corner frequency. So you have two corner frequencies here. Now our aim is to assume two more corner frequencies lesser than omega c1 and greater than omega c2. This is a procedure which we normally follow in a body diagram. So I assume that omega L is equal to 0.1 and omega h is a little higher than 5, which is 10 radians per second. It is not mandatory that we should choose only 0.1 and 10. The condition is omega c1, the omega L should be less than omega c1 and omega h should be greater than omega c2. That's it. You can choose your value as your wish actually. There is no other constraints available. Only this condition has to be satisfied, right? Then we go for forming the table. The terms available is 8 by j omega, 1 by 1 plus j omega, and 1 by 1 plus 0.2 j omega. This is being arranged based on their time constant form or corner frequencies, we can say. So the first term is 8 by j omega, which doesn't have any time constant, so there is no corner frequency available there. And since omega is in the denominator, it will have the slope will have a minus term, and the power of omega is 1, so you'll have a 20 there. So minus 20 is the slope of this particular term. And since there is no change, this is the first term, and there should not be any change in slope. Then we go to the second term based on the corner frequency. This term should be chosen in terms of the corner frequency in ascending order. That is, the lower term first, then the higher term, followed by the higher term. So 1 by 1 plus j omega term has a corner frequency 1. So we choose it in the second bar. Now you can see that it's again a first order system which is there in the denominator. So you'll have a slope of minus 20. Already you have a minus 20. The change in slope will be adding these two. So you'll get minus 40. Then the third term based on the corner frequency is 1 by 1 plus 0.2 j omega. Now the corner frequency is 5. So obviously this is also a first order term which is the available term is in the denominator omega. So you have a first order term, so minus 20 there. Already we have a 40 minus 40. Add these two, get to a change in slope, we get a minus 60 there. Then calculating the magnitude value for every corner frequencies, we are supposed to find what is the magnitude value. So when omega is equal to omega L, which is equal to 0.1. So for a constant term to be chosen first, 8 by omega. So it is going to be 20 log of 8 by omega. So 20 log of 8 by omega, instead of omega, you substitute omega L, which is 0.1. So you get a value 38. It is 38.06. You assume it or equivalent value chosen to be is 38, round off it. Then you go for the next corner frequency, omega is equal to omega C1. Now you start with this particular slope. So minus 20 log of the present corner frequency value is 1 and the previous corner frequency value is 0.1. So present by the past minus 20 log of 1 by 0.1 plus the previous magnitude value 38. If you manipulate that, if you calculate that, you will get a value of 18. Now you go to the next corner frequency choosing out. Then the slope chosen will be minus 40. The present value is 5 corner frequency value. The previous value is 1. So minus 40 log of 5 by 1 plus the previous magnitude value 18. I'm getting minus 9.95. Rounding out, you will get minus 10. Then the last corner frequency, omega is equal to omega h. Now I will be choosing the corner, the slope value as the last slope minus 60. The present omega h I have chosen is 10. The past value is 5. So minus 60 log of 10 by 5 will minus plus the previous magnitude value minus 10. So I am getting a value around minus 28. So choosing the magnitude value to be minus 28. So your magnitude calculations are over. Then try to calculate what is the phase angle value. Now you see the transfer function. This doesn't have any phase angle. This will have a minus 90. This have minus tan inverse of omega, and this is to be minus tan inverse of 0.2 omega, which is available as minus 90 minus tan inverse of omega minus tan inverse of 0.2 omega. Form a table, vary the omega value, use your calculators to calculate, substitute the values of omega chosen in this equation so that you get different values of your angle. Now you can plot both your magnitude values and your phase values in your body diagram and check for the stability. So the first value at 0.1, the value is around 38. So I have chosen it 38. This is 38 actually. I can write it. So the point is 38. Okay. Then at 1, the value is 18. So you are getting an 18 value here at this point. At 5, you are getting minus 10. This is 5. This is 1, 2, 3, 4, 5. So I am getting this is 5 actually. At 5 radians per second, I am getting minus 10 magnitude. At 10, I am getting minus 28. I hope so. So I am getting a minus 28 point here. So I have drawn this. Now you are joining it using scale, and then putting out the slopes which is available minus 20, minus 40, minus 60. So your magnitude plot is over. Now you have to plot your phase plot from the table. You are getting a plot like this. Now finding out the frequency domain specification. And what is the frequency domain specifications? Mainly we focus upon the stability based analysis. So we go for phase margin and gain margin. Now calculating the phase margin, how to calculate this phase margin? See your magnitude plot where it crosses your 0 decibel line. It is crossing your 0 decibel line here. Extend that point down. It will cut your phase plot at some point. Correspondingly, what is the phase angle value? I have got it like minus 189. So your phase margin formula is gamma is equal to 180 minus 5GC minus 5GC, and the 5GC value you got it like minus 189. Okay, so you are substituting that. So 180 plus 5GC. So 180 plus 5GC will get minus 189 substituted here. You are getting minus 9 as your phase margin. Since you are getting a minus negative value as your phase margin, the system is unstable. Okay. Uh, Also, we are supposed to find what is the specification provided. So calculating the specifications. So it is all the specifications are provided in time domain. So you convert that into frequency domain. It is provided that zeta value is 0.3, the damping factor value. Settling time for 5% of tolerance band is being provided as 12 seconds. So taking out the formula, settling time is equal to 3 by zeta omega n. The unknown value is omega n. Calculating that, we are getting omega n is 0.83 radians per second. Then based on the zeta value, you are supposed to find what is your phase margin. So gamma is equal to 180 plus 5GC is your phase margin formula. This 5GC, that is the gain crossover frequency angle, can be found using the formula tan inverse of 2 zeta by UGC, U suffix GC. What is U suffix GC? U suffix GC is the normalized gain crossover frequency. The formula for that is minus 2 zeta squared plus square root of 4 zeta power 4 plus 1, the whole power 1 by 2. Now you replace this value here, you obtain a formula to find what is your gamma value. Your zeta is being provided as 0.3. Substitute that here. You'll be getting zeta gamma is equal to 33 degrees. But for an uncompensated system, what is the gamma value we are getting? The gamma value what we are getting is minus 9, which is not reaching out your specification. So the system is unstable. It is supposed to find what is the to make the system stable, you are supposed to follow the design procedure of a lag compensator. So that is what mentioned. Since the phase margin is negative, system is unstable, so compensator is required to make the system stable and to satisfy your desired specification. The transfer function of the lag compensator is S plus 1 by T divided by S plus 1 by beta T. The unknown variables are T and beta. You are supposed to find the values of T and beta so that you can design your lag compensator. The first step to be followed is finding out what is the new gain crossover, new phase margin from the provided formula. It is gamma D plus epsilon. The gamma D is nothing but desired phase margin which you have calculated, that is 33 degrees, and epsilon is normally chosen as 5 degrees initially. Once the condition is being checked and still the specification is not reached, then you add another 5 degrees here so that you make it 10 and follow the same procedure and check whether again your specifications are met. So we start with the initial value of 5 degree first. So now your new gain phase margin is 38 degrees. From this gamma n, using your gain margin formula, find out what is GCN, because gamma is equal to 180 plus 5GC. So using this, you try to find what is 5GC, new gain phase margin, what you call as gain crossover frequency angle. It becomes gamma n minus 180. Gamma n has been already found, so you get minus 48. Now go to your body diagram. You choose what is minus 142. This is minus 142. This point as minus 142. Your omega GCN, that is your gain crossover frequency, is 0.9, which is nearly around 1 actually. Okay. At that value, your gain is also being calculated as something around 2. Something around 2. You will see, continue the procedure. So from the graph, we found omega GCN is 0.9 radians per second. And at that time, the AGCN is equal to, is it actually 20 there? Yes, this is 18, so this is 20. So you'll get a 20 here, AGCN value, it is not 2. So the AGCN, these are all from the graph. AGCN value corresponding to this value 0.9 is 20 decibels. You have a formula, AGCN is equal to 20 log of beta, finding out the beta which is unknown. AGCN is known, beta is unknown, so you get beta is equal to 10 using this. Take anti-log on both sides, so you'll get 10 power AGCN by 20, so 10 power 1, 20 gets cancelled, so 10 power 1 is 10. So you have a thumb rule to calculate your T, always 1 by T is equal to omega GCN by 10. So now you can calculate T is equal to 11.11 using this omega GCN formula. So T is equal to 10 divided by omega GCN is the next formula. We are getting T is equal to 11.11. Already you found what is beta. Now beta T is to be found so that you can replace that in your transfer function of the compensator. So 111.11. Now you substitute that, take it to the formula of time constant. So you put your compensator in cascade. So it is 1 by T. It is 1 by T divided by 1 by beta T. So I am getting, like, if you take this outside, I am getting 1 plus ST by 1 plus beta TS. So replacing that, I am getting 11.11S, 111.11S. I can find this as the, we will discuss about the larger time constant available, and still the design is not correct actually. But initial stage, we will check whether your phase margin is being satisfied. Then we will get inside the higher value of time constant. Okay. So to remove this attenuation factor, you add this 1 by 10 here in cascade. So 10 gets cancelled. Now this entire transfer function is the overall transfer function, and for this overall transfer function, you are supposed to find the 5 GCN, putting out your omega GCN and calculate your gamma. So this is your overall transfer function. Check whether it is in time constant form. Yes, it is in time constant form. Convert that into j omega form. Write your phase angle equation. So gamma phi is equal to tan inverse of 11.11 minus tan inverse of 111.11 omega minus 90 minus tan inverse of omega minus tan inverse of 0.2 omega. Now replace omega with omega GCN, which is already found as 0.9. Here omega GCN is found from the graph. Yes, here 0.9 radians per second. You replace that here. I'm getting 5 GC naught is equal to minus 147.33. It is almost near the required phase margin. Even though the time constant is found to be a little higher, which makes your response little sluggish, you are able to reach the gamma value specified, which is 33. Even if you want to improve that, to reduce your time constant, what you have to do, again you have to add another 5 degree here, so it becomes a 10 degree here. So 33 plus 10 will give you 43. Put here, you will get a different value. You proceed with the same procedure steps. You will get a different gamma value, which will be little higher than this, and the time constant value will not also be little higher. So the only problem with this design, you are able to reach the face margin, but the problem is your time constant is a little higher. To minimize this, you can also repeat the procedure by changing a 10-degree value instead of a 5-degree, and do the similar steps followed in the previous procedure. And finally, you will get a different compensator value and an acceptable specification. That's right. So this is how a lag compensator should be designed, and you can see that nearly 10 to 15 minutes. Um, it will take, if you are thorough with the formulas and the procedure, it will take another it will take 20 to 15 to 20 minutes to solve this problem. And if you are practicing it a little more, which will make you know the procedure easily, and as soon as you get the problem, you will know the formulas, you remember the formulas, you will start doing it. So kindly practice some more problems available from the textbooks, whatever you have for control systems. And if you have any clarifications or doubts in this particular video or some other problems video, you kindly contact my WhatsApp number, or comment in the comment box available in the YouTube channel, so that I can notice that and make your doubts clear. So we will meet in the next video. Thank you.